this is our physical picture of an atom that we first started out with. There's a nucleus in the middle, and then there are electrons flying all around. What we've been doing for the first two periods for the first period of this week is we've been studying the electrons. That is to say, the electrons they jump between energy levels and they give off light, and they're kind of like a squishy ball, so the mechanical properties, and when an electron jumps to another atom, you have a molecular bond and all of that. But also in the nucleus, also in the atom, there's a nucleus. And the nucleus is utterly tiny. It is, this dot here is much too large. The nucleus would be smaller than a pinprick here, yet it contains 99.99% of the mass of an atom. It's basically all of the atomic mass is in the nucleus. The electrons have actually a very small mass compared to, say, a nucleon. Now, so, because it's smaller, in fact, the energies of the things inside are much higher. And that's counterintuitive, but that's the way it is. You squeeze down on a quantum system, the energies of the things inside go way up. So, inside of here are very energetic particles that have like 1 million times the energy of the electrons here. So when you calculate an angle from your diffraction grating, and you measure a wavelength, and from the wavelength you measure an energy, these energies are like typically electron volts, but the energies of the nucleons inside of a nucleus are millions of electron volts, okay, million times as much. That's why nuclear energies are vastly larger than chemical energies or atomic energies. So, now, as you know, when electrons jump around in here and they send out light, we call that a photon, okay? So a photon comes out of here. We call it a photon. It has an energy of a few electron volts and so on. And that's called a photon. But however, you know, a nucleus also sends out photons, and they're called gamma rays. So that's the third letter of the Greek alphabet. It's called gamma rays, okay? And gamma rays are actually very much like X-rays, but even higher energy. So they're the same thing, but the energy is 1 million times higher here than it is here, okay? And so we can measure these gamma rays coming out. Now, in addition, as we'll see when we do static electricity, we can strip an electron off of here, and we call that ionizing this atom. But you know, a nucleus also spits out an electron, and this electron, when it comes from a nucleus, we call it a beta ray. Well, so I'll use the Greek letter, beta ray. That's the second letter of the Greek alphabet. A beta ray is just an electron that came from the nucleus. An ionization electron is an electron that came from the electrons around the atom. Okay? So these are both particles that come out of a nucleus. Okay? Beta rays and gamma rays. There's a third particle that comes out of a nucleus. And I'll write it this way. I'll write it this way. It is, in fact, what's called an alpha particle. Okay? Alpha particle. An alpha particle is really a helium-4 nucleus. That's what it really is. It's a helium-4 nucleus. 2 neutrons, 2 protons bound together make it an alpha particle. And again, the energies of these alpha, beta, and gamma are millions of electron volts. So we have a Geiger counter over here, and we can measure some of these.